Okay, 9.2, differential equations with initial conditions. So recall that the position function, s of t, has a velocity function, v of t, given by its first derivative, and an acceleration function, a of t, given by its second derivative. And if you're given the velocity of a particle, you can then use integration to work backwards to find the position function. Remember, integration is anti-differentiation. Take the antiderivative. Likewise, if you are given the acceleration of a particle, you can use integration to find its velocity function and then do it again to find its position function, provided we're given some sort of initial conditions so that we can find those c values, those plus c's. Now, thinking about time-dependent processes, usually the initial start time is at t equals 0, okay? So that's typically our initial start time, okay? So what we're going to be looking at is we're going to use the initial conditions to solve for the constant in each function. And we're always going to work in terms of the variable t. We're working backwards from acceleration function to the velocity function, and then from the velocity function to the position function. So think about what we did back in chapter 2, I think it was. So we are looking at, we have the position function, and then we took the derivative of the position function, gave us velocity, and then velocity's derivative gave us acceleration. So if we're working towards acceleration, we're taking the derivative, as I tried to write sideways. And if we're going from acceleration back up to the position function, this is where we're going to integrate or take the integral or take the antiderivative. Pardon me. Okay, so we're working in this chapter, obviously, on the antiderivative or integrating. Okay, so example 1, we're going to solve ds dt equals 2t. So this is what we call a differential equation. Okay, this is our differential equation. And what this tells us is it's the derivative of the position function with respect to time. So we actually have to recognize that as the velocity function. So this is the derivative of the position function with respect to time, aka that's velocity. V of t is equal to 2t with some initial conditions. So they're saying with the initial condition s equals 3 when t equals 0. Okay, so we have to think back to 9.1. How do we take the antiderivative of v of t? So if we know, we just have to go back 1 to find s of t. So s of t will equal to, we add 1 to the exponent and then divide by the new exponent. So s of t will equal to t squared plus c. So don't forget your plus c. I should probably include it in that spot too. And then the next thing is, so this is kind of step 1. Now that we have some conditions to work with, we're going to actually solve for the c value. So the next thing to do is to know that when s is equal to 3, t was equal to 0. So then we can say 3 is equal to 0 squared plus c. So c is obviously 3. And then we can state our position function as our last thing that we do. Therefore, s of t is equal to t squared plus 3. And so now we have a way to solve for that constant. Okay, example 2. Determine the equations for velocity and position given a is equal to negative 9.8 meters per second squared with initial conditions v equals 10, s is 200 at t equals 0. Now, I know you physics peeps are annoyed by this because you're used to negative 9.81. So I apologize, but we have negative 9.8 for most of our calc questions. Just deal with it. It's all good. You can be mad at me. It's okay. I'm big. I can take it. Okay. Number 1. If I know that A is equal to negative 9.8, I can take the antiderivative of that to find the velocity function, which would be negative 9.8 t plus c. Okay? But what I now know is that when v equals to 10 at time 0, not what I just said. At time 0, v equals 10. So what do I know about c? So therefore, 10 is equal to negative 9.8 times 0 plus c. So therefore, I know c is 10. And I now know my complete velocity function. Okay, so therefore, v of t is equal to negative 9.8 t plus 10. I have to finish this completely before I can then take the antiderivative again or integrate again to go to the position function. I need to know what that constant value is. Okay, so it's asking for position function. So I'm going to now go and say, if I know v of t, then I can find s of t. And I'm going to add 1 to my exponent on 10, or t. I don't know why I want to call it 10. Divide by that new exponent, plus 10t plus a new constant, which I'm going to call d, because it's likely not going to be the same as the c value we found in the previous step. Okay, so when I tidy this up, I get that s is equal to negative 4.9 t squared plus 10t plus, I'm having problems writing today, plus d. Okay, and then what do we know about this? We know that s is equal to 200 at time 0. And so d, hopefully you can see, is obviously 200, but let's substitute it in. So 200 is equal to negative 4.90 squared plus 10 times 0 plus d. So therefore d is equal to 200. And I now know that I can write my position function. Therefore, s of t is equal to negative 4.9 t squared plus 10t plus 200. Awesome. All right. Next question. Determine the position function s if v is given as 1 minus 2t to the negative 3 and s equals 4 when t equals 1. Okay, so this is obviously not at time 0, so it's not technically an initial condition, but it for sure gives me an ordered pair to work with to find my constant. All right, so first thing that we're going to do is take the antiderivative of the velocity function to find t. So I'm going to find s. Okay, s is equal to 1t minus 2t to the negative 3 plus 1. That gives me negative 2, so I'm going to divide by that exponent plus c. And then I'll tidy that up. So this is equal to t, negative 2 divided by negative 2 is plus t to the negative 2 plus c. And so what do I know? I know that s is equal to 4 when t is equal to 1. So the next thing I'm going to do is substitute that in. So 4 is equal to 1 plus 1 to the negative 2 is the same as 1 on 1 squared plus c. And so 1 plus 1 is 2. So 4 is equal to 2 plus c. C is equal to 2. And then I can just write my position function. Therefore, s of t is equal to t plus t to the negative 2 plus 2, or perhaps you prefer to write it as t plus 1 on t squared plus 2. Either would be correct. Okay. I'm going to pause the video here, and I'm going to let you try examples 4 and 5 on your own. See how it goes, and then come back and check in video number 2 to see if you got them right.